this sphere, and you see the points were randomly sampled in this sphere, and the one electron is coming out in green. So this yellow are the starting points of these electron sources which were sampled inside the sphere, and this green is the electron getting out of this spherical space or volume. And let's check the cylindrical one. You'll find almost the same thing, that the particles were randomly sampled inside this volume. You see, in this outer region and this central rod of the seed. And our seed also looks very similar to this design, the OncoSeed iodine 125 design that we are using. So now returning to the other wall. So similarly, you can check other types like the emittance source is another type which you may want to include if you are interested in getting other type of shapes of your source, then you can use this kind of source, that is emittance source. And yep, you can get whatever shape type you want by just using this type of source. And then is environment source. Environment source basically is to provide an environment of radioactive environment outside any kind of object. So it's basically like an if you are simulating an experiment that includes spacecraft in a radiation belt, or a robot in a damaged nuclear reactor. So this type of source may be useful to you, but I haven't used ever this kind of source for my simulations or research work. Yes. Okay, and the isotropic source is the a point source that emits radiation in all directions. So yeah, you can define use this. Probably they have used here also the source type. It's no, it's volumetric only. Mm. But yeah, you can I so isotropic sources can be defined point source, or you can use this type of source within a volumetric source, or you can use it. And yep, we have already checked the volumetric source. And phase-space sources are basically when you divide your simulation into several parts, like if you are doing a simulation for Linux, and you want dose distribution in water phantom. So simulating uh, complete geometry that includes the Linux head water phantom will be too can be too heavy for your computer. So generally what people do is they score a phase space. Phase space generally contains information about the position of the particles, energy of these particles at a particular plane, and then you can reload this file as a source file in your another source where in another input file where you are calculating the dose distribution. So this phase space file can act as a source for you, and you will be able to do the simulation in two stages and much more easily than doing everything in one go. And there are like websites where you can find phase spaces, like if I show EA phase space directory, phase space directories. So you can database. So yeah, so here like you can download the phase spaces of different Linux, or like you see there is a Cyberknife, Electa Precise, Primus, Varian Clinic. So if you want get simulations or run simulations, you can directly download these one of these phase space file and use it as a source in your input file and for this kind of simulation. So uh, and in this case, like if you use these phase spaces, so you don't need to simulate the Linac head. All you need to simulate is your water phantom, and follow the documentation from this website, like where to place your phase space. So phase space positioning is important in this case. Yep, you can do this like x-axis, y-axis, z-axis. Yeah, that's it for this. And they are also mainly talking about Linux heads because phase-space files are mainly used for that purpose. Okay. And apart from that, like once you define your sources, then you may be interested in like simulating only fixed particle type, like only electrons or only photons, or like with the particles of specific atomic mass, particle except specific atomic mass, specific atomic number, or not other than specific atomic number, kinetic energy. So uh, y- it can be useful for you sometimes when you want to differentiate between like which particle is depositing more energy, which particle is depositing less energy, or how much is the energy deposited from the photons and how much is the energy deposited from the electrons. So this kind of filters can be useful to you, and yeah, you can feel free to use them if you need them. Okay, so do you have any questions on the source type, or like
Nothing is okay so far.
okay, because we already saw this last time, but I wanted to redo it because your internet connection was not that well, not that good as last time. So okay, so now we talk about the physics settings. Let's first go through one example on physics setting, how it works. So there are like several physics settings possible. Here is a one example where they have shown like the type is gent for modular. So if you see the physics, and they are basically modular physics lists, and then there is a reference physics list. Physics list are where you mix match set of modules, like you can customize your requirement. You can customize based on your requirements, and reference physics lists are something that are pre-made, and it includes the complete list that is provided from Chain4. And like I mentioned before, if you ask why there are so many physics lists, so these are basically derived from physics theories from different physicists, and each physics list is dedicated to specific type of simulations. Like for high energy simulations, you need the different type of physics list because you are not interested in low energy photons or electrons that are emitted from there. And when you are focusing on low energy, for instance, low dose rate brachytherapy simulations, so there you are not interested in high energy of photons because they are not emitted. So why will you need those physics settings? Because if you check, you want to know which is the limit of the physics list limit, or yeah, limits under which it's simulating. For example, I show you gent for so you will get an idea like which physics list you're interested in. So where are their publications? Mm, yeah, publications. So we like you see recent developments, and we can open a PDF. So just scroll down and search for the physics section where they define, like here they define the geometries what they have included recently, and These same geometry types and these updates are also available in Topaz as well. So it's always good to check the documentation and see what they have recently updated. So for physics list, you see, here is the information that we are interested in. So there is a model. This is the process that simulates these particles, and this is the model and the energy range they cover using these physics list is this. So electrons, you see different uh, physics list model is considering different energy range. The same particle is getting simulated. Like electron positron Bohr-Baba model simulates from 10 keV to 10 tera K electron volt. Similarly, for Penelope, it's 0.1 keV to uh, 5 giga electron volt. So you have to be very careful when you are selecting your physics list, like which is matches your requirement and how you're going to deal with it. And it's best first to check on the developer website, or like Giant Topaz is repped on Giant4. So you look into Giant4 website or publication, recent publication, like which energy range I'm simulating, which physics list falls in this, covers this range, and then you can take that physics list. And then if you are want to you are simulating something on brachytherapy, look for a brachytherapy uh, simulated paper and find out which physics parameters were they tuned, and then that can be the baseline for your start, or the starting line for your simulation, because now you have already done basic tuning of your physics list. Otherwise, other method is hit and trial. You keep on trying different physics list and other settings, like cut for gamma, cut for electrons, we'll check to it, and cut for positrons. Like you don't want to uh, simulate these particles if they have a range less than this. So these kind of things you generally get from literature, and if you don't get from literature, hit and trial may take longer. Okay, now getting back to the physics list. So here, like we saw, they have two type of physics list. One is the reference type, and another is the modular type. So reference type is pre-made. You don't have to do anything, and the modular type is you can mix the reference physics list and make your own. The other is the optical physics list, is for optical physics simulations. Yeah, so less processes. If you make this, when you will run your simulation, they will print what processes you have selected for your simulation. And yep, so there is this modular physics list like we discussed. So let's see the example. Here is Giant for, they are considering the type is Giant for modular, and the modules they are considering is the decay of a radioactive radioactive atom isotope, G for decay. Then they are using standard option 3, like if you see the paper, there will should be something on option 3. Mm, not here. Yeah, you see, like what type of application. Here they provide information on which um, physics list is for which application. For instance, here is like standard physics is for high energy physics. uh, EM standard physics option 3 is for space and medicine, and For EMDNA physics is for DNA simulations or DNA break simulations if you are
Mm-hmm.
doing nanodosimetric simulations. So it's like I said before,